I am a number theorist. I work in IISc. Number theory is a very old branch of mathematics. The questions that one deals with are solving equations for integer solutions. So you look at Diophantine equations, so polynomial equations, and you seek solutions in integers. Modern algebraic number theory involves a very sophisticated technique. So there are a lot of invariants or other functions that one attaches to these Diophantine equations. And my specific research concerns in studying arithmetic or these equations through what are known as L functions. These are complex analytic functions that surprisingly encode a lot of information about these equations. And the precise conjectures that one makes codifies these relations are called main conjectures in Iwasawa theory. So my main work has been to prove these main conjectures of Iwasawa theory. Iwasawa theory is a systematic tool for proving conjectures of the nature where you relate L functions to arithmetic. Classical Iwasawa theory deals with an infinite tower of number fields where the symmetries of these number fields are commutative or abelian, which means that it doesn't matter which order you apply the symmetries in. The questions arithmetic of elliptic curves and so on naturally leads to extensions where the symmetries are non-commutative. So it matters in which order you apply these symmetries. And so non-commutative Iwasawa theory developed through late 90s and early 2000s into a vast array of conjectures, and my work is resolves this conjecture in the simplest case of Tate motifs. So it provides a first concrete evidence that non-commutative Iwasawa theory is useful to study arithmetic, and the conjectures in case of other motives are perhaps true. There are two parts to my work on non-commutative main conjecture. One is a very algebraic part where I studied what are called Iwasawa algebras of non-commutative p-adic groups. This algebraic side of my work involves describing these Iwasawa algebras or a family of Iwasawa algebras explicitly in a precise sense, and that was the first part of my work. What that algebraic part does is it predicts a certain congruences between L functions. There are precise relations between distinct L functions that should be satisfied. This is what the algebra predicts. And the second part of my work involves actually proving these precise relations. And these I managed to do using modular forms. Gross-Stark conjecture is again a conjecture about L functions, the p-adic version of L functions. It was made by Gross in the early 1980s. He described the leading term of p-adic L function at s equal to 0 in terms of some very precise arithmetic data. This conjecture had been open since 1980s until a breakthrough was made by Dasgupta, Darmo and Pollock in about 2010 in the rank 1 case. But at that time, higher rank case seemed inaccessible. Samit Dasgupta was visiting me in London one summer to discuss some mathematics, and we started talking about Gross-Stark conjecture, and a breakthrough came a few months later when we discovered a particular matrix, and vanishing of determinant of this matrix gives Gross-Stark conjecture. So conceptually this proof is very different from the rank 1 case. So Brumer-Stark conjecture is again about L functions, but it's a bunch of L functions that are packaged together in what is called a group ring over integers. So it was known that to resolve Brumer-Stark conjecture, one has to work over integers. And you can imagine that if you want to solve equations, linear equations just say, then they would be much easier to solve over rational numbers than over integers. Working integrally is harder if you want to solve certain equations. Now, our work on Gross-Stark conjecture, it bypassed some of these very delicate calculations that appeared in the work of Dasgupta, Dharma and Pollock. And so it seemed plausible that one could make these techniques work integrally. And so when I was visiting Samit in Duke, we started discussing Brumer-Stark conjecture to see how far we could push our techniques and get something towards Brumer-Stark conjecture. But there were a lot of major obstacles to overcome. For example, what are called trivial zeros of p-adic L functions. These are really very hard to get a handle on, and we managed to do that. This was kind of beyond our work on Gross-Stark conjecture. But the main impetus to work on Brumer-Stark conjecture came through our method of solving the higher rank Gross-Stark conjecture. I think mathematics is a different language, as you may have heard many people say. And as with learning any language, one needs patience and to learn the basics of the language, and only then you can go ahead and read what's written in this language. So often the mistake I think that one makes is try to go to the end product rather than learning the language. The second thing is, as with any language, it helps to speak. So often explaining something to other person tells you what you may not have understood. Right? So if you try to explain a solution, just a standard high school problem, if you just try to explain it to somebody else, maybe you understand it better. And this in fact happens at all levels, even at a research level. You try to explain it to other, and that's how you build collaborations. So I think talking mathematics with other helps a lot. My first reaction on winning the Infosys Prize was of course elation. But also I knew that Andrew Wiles was on the panel. And an immediate thought that came to my mind is that this is a recognition from Andrew Wiles. All of my work has its origin directly in Wiles's work. I mean, his work is of course much vast. I only am building on a small part of it. But that was my immediate reaction, that wow, it's kind of Andrew Wiles is recognizing my work. About how it would help my research, well, I mean, one would like to think that motivation for mathematical research just comes from within, but it is also good to get recognized by one's peers for what you are doing, and so that's also motivation to keep working harder.